Hey guys, even in a normal semester at this time, it's easy to start feeling like all of these academic facts are just randomly piling in and how do they fit together and is it really worth it and what purpose do all these things have? Proverbs 24 says, "By wisdom a house is built, and through understanding it is established. Through knowledge its rooms are filled with rare and beautiful treasures." This house could probably be a lot of different things, but one of the things is our lives, our minds. If it's received correctly, I believe knowledge is an inherently positive thing. And so the more the better. And as these academic things are coming in, we'll just have to trust God that He'll put them in the right places. But you are bettering yourself, and therefore you're bringing glory to God by learning, by becoming a more knowledgeable person. This lesson is going to be about section 7.5. We're going back into chapter 7 and picking up a section that we skipped quite a while ago. So the notes are section 7.5 part 1, because there might be a part 2 coming soon, and using a worksheet, section 7.5 bears. Here are the notes, and the topic is inference for regression. Let's just jump to an example where we'll first review multiple regression that was in section 7.4, but that was much, much earlier in the course. So the problem says, okay, here in the spreadsheet, we have body measurements from a sample of young bears. So things like head length, width of head, neck girth, how far is the neck around, overall length of the bear, how far around is the chest, and what does the bear weigh? And you might say, big deal, but believe it or not, there are people, zoologists, whose job it really is to study such things. For example, if people are administering a national park or other wildlife reserve, they might want to know something about the health of the bears in the wild. A model to predict weight from the other measurements would be useful. So if you're collecting measurements like this, bears don't cooperate. So typically what's done is they're anesthetized, shot with a tranquilizer dart, and then body measurements are taken before the bear wakes up. Well, it's pretty easy to take some of these other measurements while the bear is just lying there. You can measure the length of its head or its width of its head or whatever. But bears that are sleeping don't climb on scales, and so it's difficult to take their weight. So if we had a model that gave the weight as a function of other quantities that were easier to measure, that could be useful. Find a model giving weight as a function of head length. So we could run linear regression from the data analysis menu. I'll do an example in just a moment, and get this printout screen. And remember, at that point, we were coming down here and picking off the coefficients and taking them and writing them in a regression line, a regression function like this. We were also interested in the adjusted R squared. So this model using head length can explain about 69% of the variation in weight. Now, that's not bad, but we might want more accuracy. We have a lot more data, right? We have all of these other measurements in addition to head length. So the next thing to try might be, let's throw everything at it. Let's give weight as a function of all of these other measurements. So a reminder how to do that. Data analysis, choose regression. For our Y range, that's our dependent variable weight. For our X range, that will be all of these variables. I include the labels in that, and I'll have Excel put the worksheet in a new tab. So that's how I got the output screen that's on the notes here. And we use it the same way. Come here to the coefficients and pull off all of these numbers. Be sure to keep them in their associated with their right variable. So here is a model that gives weight as a function of head length, head width, neck girth, length, and chest girth. And the adjusted R squared has now gone up to 94, 95%. So this model explains a lot more of the variation in weight. Question, which model is better? And I put better in quotes because better is a subjective thing. So there are two ways of answering this question, at least two ways. One is, which is simpler, and of course that's far simpler to just use head length. If you're thinking about using this model, then you're going to tell these zoologists to say, okay, every time you anesthetize a bear, you need to measure all of these things. Whereas in this model, you're saying, okay, just measure its head length, which you might even be able to estimate visually by through binoculars or some safe way. So much simpler to use model number one if it were accurate enough, but it might not be. So most accurate model is to use all the variables. And so we're pulled both ways. We want both simplicity and accuracy. These models are fighting against each other in terms of their strengths and weaknesses. Let's save that thought. We'll come back to it in just a moment and go on to talk about something closely related here. And that is the difference between sample and population when we're talking about correlation. Here is a scatter plot. On the x-axis are people's net income in the year 2016. On the right is a self-rated evaluation of happiness. So on some survey, people were asked how happy they were. And here is the data from a random sample of 20 people. You can look at it and clearly see that there's positive correlation here, that in this sample, at least, the wealthier people tended to say they were happier. In fact, the R squared for this is 0.67. That's not the end of this story. It turns out that this particular sample was taken from this particular population. So if you're on, it's a little hard to see, but if you're on an image that has color, these are kind of maroon colored dots, and they're still scattered in here. But the other blue dots were part of the population that didn't get sampled. And so if I look at all of these as the entire population, there's not much pattern at all. In fact, here R squared is almost 0. This can happen in life, that there's almost no correlation in the population, but just by luck of the draw, I happen to get the maroon colored dots which have this pattern by themselves, and then I think that there is correlation. There is correlation in the sample, and I'm tempted to think it would be in the population. Or the other way around can happen too, that there would be in a different picture, there'd be a lot of correlation in the population, but just by luck of the draw, my sample would end up looking scattered and circular, and I would not get correlation in my sample, even though it was there in the population. So there's a difference. Does strong correlation in a sample mean there's strong correlation in a population? The answer is neither yes nor no. The answer is not necessarily. We don't know. At least not for sure. So let's get some notation here. When I take a sample and calculate the sample regression equation. Well, let's call that y hat equals b0 plus b1 times x. This is what Excel is computing when we ask it to do something like this. Here is the number b0, here is the number b1 times x, the independent variable. But if I had access to the population, I could calculate its regression equation for the population as well. And so it will be different. The population and the sample are not the same thing. So the regression equation would no doubt be different in that case. So we'll write it with similar notation, but let's use Greek letter beta when we're talking about the population. And we'll say that y hat equals some number beta 0 plus another number beta 1 times x. So this would be giving weight as a function of test of head length in the population. Now back to our question about correlation. What will be true about the population regression equation if there is correlation between the independent and dependent variable, in this case, between head length and weight of the bears? So now let me reuse these pictures for different purposes. Forget about where they come from. If I look at the left picture, there is clearly a positive correlation. Well, first of all, there is correlation here. It's positive. The regression line would fit through here something like this. And the thing that I want to talk about is what this has to do with regard to slope. I can get my pen working here again. When we look at the regression equation like this, notice that here's the y-intercept, this beta 0, and the thing that's multiplying the x is the slope. Beta 1 is giving us the slope of the regression line. And in this picture, it's clearly a positive number. The important fact for us now is that it's a non-zero number. Whereas over here in this picture, if I had Excel calculate a regression line, it could do it, it would do it, but there's no real pattern here, and so most likely it'd end up being something just kind of flat like this, where beta 1 is basically equal to 0. This line has 0 slope. And so one way to check if there is correlation between my input and output is to check whether the slope of the regression line is 0 or not. Okay, so I want to know whether beta 1 is 0 or not. Can we calculate beta 1 though? No. Beta 1 comes from the population, and I almost never have access to the entire population, usually just a sample. So no, we don't have the entire population. Well, what can I do about that? Could we calculate B1? What was the difference? B1 was the slope of the regression line in the sample. That I can do. In fact, for my example, I did it. Here, B1 was the number 48, basically. So yes, Excel will be happy to do that. And then, thinking about what we've recently talked about in terms of hypothesis testing, the thought comes to mind, well, could we use B1, our slope on the sample, as an estimate of beta 1, our slope in the population? And yes, that's as good a guess as any. It's probably a good guess, actually, but accuracy is uncertain. Beta 1 is not going to be the same number as B1, so I can guess, but I should be prepared for the fact that my guess is not perfectly accurate. On the other hand, I don't really need to know the value of beta 1 so much. I'm interested in whether it's 0 or not. So how can we decide if beta 1 is not equal to 0? Well, we have a guess for it. And so this is time for a hypothesis test. And so this is why I've waited until now in the course to talk about this material from chapter 7, because now we know about hypothesis testing. We're going to have a null hypothesis and an alternate hypothesis. I think actually I'll put them right here. A null hypothesis and an alternate hypothesis. If we go to the alternate hypothesis, it's always a statement of inequality that something is different or related or new. And so this is going to be the hypothesis that beta 1 is not equal to 0. That leaves the null hypothesis to be that beta 1 equals 0. So in the context of this problem, what's being said, beta 1 equals 0 means x and y are not related, linearly related. And beta 1 would be that x and y are linearly related. So I know how to set this up now, and then it's a matter of calculating a test statistic and a p-value and comparing to 0.05 and making a decision between these hypotheses. So now it's time to come back to these output screens and gather more information. This is a big screen of information that's coming back from Excel, and we've only used a little bit. Let's use some more. Is head length a statistically significant predictor of weight? The place to come now is right here. So I'm coming to my variable head length, and I'm going over to where the p-value is located, and I see p. And in scientific notation, it's 4 times 10 to the negative 38. Okay, this is basically 0. 10 to the negative 38 is an astoundingly small number. In particular, that is certainly less than 0.05, which is what we usually use as a level of significance in hypothesis testing. And so we reject the null hypothesis, which was that there is no linear relationship, and conclude, yes, that we do have evidence of a relationship. So answer to the question, is head length a statistically significant predictor of weight? Yes. This has implications for your project and for statistical practice in general. The fact that I have significant evidence that weight is a significant that head length rather is a significant predictor of weight means that probably in my model I would want to use head length. It's valuable information in being able to predict weight. What about my other model where I used all 1, 2, 3, 4, 5 independent variables to predict weight? What about statistical significance there? Well, now let's go to our same output screen and pick off these numbers. So ignore the intercept. That is for beta 0, and typically we don't care so much about that. But these p-values here are interesting. So I take them one at a time. For head length, when I have all of the models together now, the p-value for head length is 0.13. That's bigger than 0.05. And so now head length, in combination with all of these, is probably not so significant. Neither is head width, but neck girth is 3.54 times 10 to the negative 6. That's small. Length, not so small, and chest girth, very small. So P is less than 0.05 for neck girth and for chest girth. And that's telling me now that when I have all 5 of these variables together, these neck girth and chest girth are the most important. In fact, in terms of statistical significance, they're the only ones for which I really have statistical evidence that they are significant predictors, that they are doing a good job at predicting the weight of the bear. And so what would I do if I were to gather all of this information and say, well, which model do I really prefer now? A simple one or a most accurate one? Well, maybe somewhere in the middle. And I could come here and say, I think I want to choose these 2 variables since they seem to be the most significant ones. So let's go back to our data sheet. And now I've decided that the 2 girths are the ones that I would like to use. When I do regression on Excel, the independent variables have to be side by side. And so if they're not, like they're not here, then I could open up a column and do some copying here so that the 2 girths are side by side. Now let's run regression. And the Y range are the weights, which is now in column H. And the X range are the 2 girth columns. So like this. Keep our labels, put it in a new worksheet, click OK, get this screen, which I have copied into the notes here. And again, I'll do a check. If I come back here and look at the p-values for these coefficients, you see that they're still both small, much smaller than 0.05. So I think I've settled on a good choice for a model to use the 2 girth variables. So now if I come here and pull off my coefficients, I would propose using the model that weight is negative 280.83 and then plus 6.61 times neck girth and then plus 9.14 times chest girth. And the adjusted R squared now is right here, is 0.943. So this model is not too complicated. It has just 2 independent variables. The adjusted R squared of 0.943, notice with those 2 variables, I can explain 94% of the variation. With all 5 variables, I could only explain 94 or 5% of the variation. So almost as good as using all 5, but with a simpler model. So this might well be the best choice, a compromise between simplicity and performance or accuracy. And we'll stop there.